We know that aircraft are designed to be as light as possible. But lightweight structures tend to be flexible, and aerodynamic forces are able to bend and twist them. The stiffness of the structure is a fixed value, but aerodynamic forces are proportional to v squared. At low airspeeds, the aerodynamic forces are small and have no significant effect on the structure. But at higher speeds, bending and twisting of the structure will be greater. Therefore, at some high airspeed, the aerodynamic forces will become greater than the resisting stiffness of the airframe, and structural failure may occur. Aircraft must be designed so that the speed at which structural failure can occur is higher than Vd, the design dive speed. We will now consider some of the effects of structural distortion, and how the designers can make the aircraft light but also strong enough for practical purposes. If an aircraft experiences an upgust, or the pilot maneuvers the aircraft, the lift will increase, and the wing will bend upwards. When the gust stops acting, or the maneuver ceases, the wing will return to its original position. But it's not just wing bending that must be considered. When distorted by an aerodynamic force, the wing will also twist. We'll examine wing twist in the next lesson. We used the aerodynamic center when studying stability. The aerodynamic center is located 25% aft, and it's the point through which we consider a change in lift to act. The wing will have an axis about which it will twist, called the torsional axis. Let's introduce a true airspeed vector and an upgust, which will result in an increase in angle of attack. The increase in angle of attack will give a change in lift, acting upwards at the aerodynamic center. But because the aerodynamic center is forward of the torsional axis, the wing will twist as well as bend upwards. The resulting increase in wing incidence will increase the angle of attack further and generate more twisting. Eventually, the stiffness of the structure will stop further distortion, and the elasticity of the structure will start to return the wing towards its original position. Unfortunately, the wing will twist in the opposite direction, and a downwards aerodynamic force will add to the elasticity of the structure, resulting in oscillation. If the oscillations were to increase, the process would be called divergence. But the design of the structure ensures divergence cannot occur at any speed less than Vd. As mentioned before, an airspeed will eventually be reached when the aerodynamic forces are greater than the resisting stiffness of the airframe. Divergence will then occur, and structural failure will follow. So, what can the designers do to increase the operational airspeed, prevent structural failure, and keep the structure light? Make the wing stiffer is the obvious answer, but that would increase the weight. A far more elegant solution is to move the torsional axis forwards, courtesy of Pratt & Whitney, General Electric, or Rolls-Royce. Engines have to be hung somewhere, and pod mounting them beneath the wing allows them to act as a mass balance weight for the wing. The weight of the engine forward of the leading edge positions the torsional axis closer to the aerodynamic center. So now, when an increase in lift occurs, the wing only bends. There is no change in incidence and no increase in the change in lift. Consequently, when the change in lift is no longer present, the wing will return to its original position without significant oscillation. The wing will oscillate slightly in turbulence, but the elasticity of the structure will not increase the motion, and the stiffness in the structure will damp out the oscillation. How control surface flutter is prevented was explained when you were studying flying controls, but we will review it here. As before, we will use the ailerons as an example. The wing is the most flexible of the structures to which controls are attached. But control surface flutter can also occur with the elevator or the rudder. If an aileron is moved down, an up force will be generated at the hinge. This will twist the wing about the torsional axis, and due to the inertia of the control surface, the aileron will be further displaced. In effect, the control surface will lag behind the motion of the aerofoil. The increased displacement of the control surface will twist the wing further. The wing is being wound up like a spring, and like any spring, its resistance to further deformation will increase, and the aileron will start to catch up with it. The result will be rapid oscillation of the control surface and wing, which will lead to catastrophic failure. Control surface flutter can be prevented by moving the center of gravity of the control surface forwards onto the hinge line. Now when the aileron is displaced, the wing will twist, but the aileron does not lag behind, the wing twist does not increase, and no oscillation takes place. The center of gravity is moved forward onto the hinge line by placing a mass balance weight forward of the hinge line. During your study of stalling, you were advised to use the rudder to keep the wings level when flying close to the stall, because use of the ailerons could make the aircraft roll in the opposite direction to your input. Before going on to study aileron reversal at high speed, let's review low-speed aileron reversal. The wing is shown at a high angle of attack, close to the stall. If this wing were to start dropping, and you use the roll control in an attempt to stop it, you would fully stall the wing, and instead of raising the wing would drop faster. The result of your aileron displacement was the reverse of that intended, hence the name, aileron reversal. And because this took place at low speed aileron reversal. Let's now consider aileron reversal when flying at high speed. When flying at an indicated airspeed of about 220 knots, a downgoing aileron will give the wing an upwards acting change in lift to roll the aircraft as intended. But, as previously described, the wing will twist in the opposite direction to that of the aileron. The aileron has increased the camber of the wing, but the wing twist has decreased the incidence of the wing, which will tend to decrease the change in lift from the aileron. At low indicated airspeeds, the wing twist will have a negligible effect on the change in lift from the aileron. But at higher indicated airspeeds, the wing twist will increase for the same aileron displacement. Eventually, a speed will be reached when the wing twist has a greater effect than that of the aileron, and the aircraft will roll in the opposite direction to that commanded by the pilot. This is high-speed aileron reversal. Obviously, an unacceptable characteristic, which would limit the maximum operating speed of the aircraft. In the next lesson, we'll see how the designers can raise the high-speed aileron reversal speed above VD, so it doesn't affect the aircraft operationally. Ailerons are attached to the trailing edge of the wing as far outboard as possible to give the longest arm to the aircraft's centre of gravity, hence maximum effectiveness. On aircraft with more than one set of ailerons, the outboard ailerons can be called low-speed ailerons. Unfortunately, the wingtip, because it is furthest from the point of attachment, is the most flexible part of the wing, and therefore most vulnerable to high-speed aileron reversal. On aircraft that would otherwise be speed limited by high-speed aileron reversal, another set of ailerons are fitted, inboard ailerons. Inboard ailerons are also known as high-speed ailerons or all-speed ailerons. The inboard ailerons are attached to a much stiffer part of the wing, so the wing doesn't twist so far at a given airspeed. This increases the speed for high-speed aileron reversal to a speed above VD. a speed never likely to be exceeded in service. The illustration shows an aircraft flying at low speed. We know it's flying slowly because the flaps are down. Both the inboard ailerons and the outboard ailerons move when the pilot initiates a roll to the left, stops the roll, initiates a roll to the right and stops the roll. With the flaps down for low-speed flight, both the inboard and outboard ailerons work. Let's raise the flaps so we can accelerate. Now when the pilot initiates a roll to the left, only the inboard ailerons move. There is a mechanism that progressively locks out the outboard ailerons as the flaps retract. And when the flaps are fully up, the outboard ailerons no longer move when the pilot makes a roll input to stop the left roll, initiate a roll to the right, or to stop a right roll. To summarize, the inboard ailerons and the outboard ailerons work when the flaps are down for low-speed flight. It is the outboard ailerons that either work or don't work. The outboard ailerons work when the flaps are down at low speed, but don't work when the flaps are up for high-speed flight. The inboard ailerons always work, at low speed or high speed. Understanding the details of your aircraft systems often has a practical value. For example, there is a known exercise that British Airways have used during a Boeing 747 flight simulator detail. Your 747 suffers an engine failure shortly after takeoff. After you've raised the gear and flaps, another engine fails. The 747 is now climb restricted at that weight with a double engine failure, and you can't clear the surrounding terrain, so you must fly down a winding valley. You will have great difficulty rolling the aircraft to avoid collision with the valley walls, and the instructor will expect you to lower the flaps slightly, to regain use of the outboard ailerons, and give the aircraft adequate roll response. Another control system, commonly used to reduce high-speed aileron reversal on jet transport aircraft, is roll spoilers. Spoiler surfaces are located inboard of the wingtip and are mounted on the rear spar, so they do not change the camber and twist the wing. They assist the ailerons with roll control by moving up on the side with the upgoing aileron and back to flush. Once again, up on the side with the upgoing aileron and back to flush. With the flaps up, they move up on the side with the upgoing aileron and back to flush. Up on the side with the upgoing aileron and back to flush. We have now finished our study of aircraft limitations and the methods used to increase the speed at which unfavorable characteristics can occur to speeds higher than VD.